So models, first class of models, we'll talk about how is the search process. So far we have a representation. How do we represent? We select the right terms. We stem, we analyze natural language. We do stemming. And we decide how important are terms based on 3 factors: term count, inverse document frequency, taking into account the frequency of a term. Frequent terms are dealt differently than infrequent terms. Third factor, document length. Okay, and all of these 3 we talked about last time, and we repeat them on June 1st. Now what am I going to do with this metrics, with these weights? How can I calculate a match value based on these weights? Last time we did it heuristically based on the sum. We always calculate the sum of the term vectors for the example Wolf and Niedersachs, remember? And today we'll see how could we do it and what are the implications and what are the problems of that. Anyway, so we move from representation, query is represented, text is represented, to the matching algorithms. And here we have 2 classes on that. The first class will deal with the traditional model, the Boolean model, and the vector space model. And the second class, June 7th then, or 8th, will deal with more advanced model language models. And today we have these 2 topics, Boolean matching and vector space matching. Okay, what are other models? There's a lot of models in retrievals, in information retrieval. A family tree based on by Nick Dalkin and Bruce Croft here. They said, okay, first we have exact match, partial match. Here we have, of course, Boolean systems. Here we can have, again, a lot of different systems. Mainly we talk about individual things. Next time we'll briefly talk about spacing activation. So we have one example for network models too. But today we'll do with exact match, with fuzzy sets, which can be could also be put as a related term here, and individual models, which are basically feature-based, which means weighting features of the terms. We'll deal with the vector space, and we mentioned the probabilistic model. Okay. So what is a retrieval model? It's a way, of course, to calculate make a decision based on numbers. What is the first, what is the second hit in a document? But if we observe it from a more broad perspective, we say, well, that's just a metaphor. It's a way to talk about search. How can we decide what is the best hit? We need a metaphor for that. Then we make a decision. So the basic metaphor, the first metaphor was set theory. This is just like working with sets. We have a set of, we have a search term, and then we have a set of documents that contain this search term. And this set, and we have maybe a second query term and a second set of terms, and then the intersection overlap is the result set. So set theory, working with sets, is the idea behind that. Of course, then we can make a more general model and move to fuzzy sets. We'll have a brief look at that today. But then the core model that we mostly will work with is a vector space model, which is also kind of a family of models, or we can use the vector space model to express other models as well. And here we have a geographic, kind of geographic or geometric metaphor. We say, okay, well, we imagine that search is like a big space with lots of documents, and we look for the closest to our interest. Our interest is also a dot somewhere, one position in this big space. And if there are documents close to our interest, closely related with a small distance, that is similar, that is a good hit. That should be the best search. So interest and closeness of interest also can be seen as a metaphor for search. And of course, closeness, distance between data points is something we can easily calculate. And that is a first approach in the vector space model. Then the probabilistic model takes this one step further, as well as probability that a certain document is relevant, and language model, something that we'll deal with on June 8th, hopefully. So we have the matching paradigm of the classic IR is Boolean retrieval, right? Something that is still active in our library, as I mentioned. Our library uses a Boolean retrieval approach. Basically, most libraries do that still. And here we have the set theory as an analogy or a metaphor. Retrieval, well, that's just like working with sets. You make intersections and so forth. And then you get your result set. And in order to do that, you express your intent in a exact retrieval language. You have to learn how to work with sets, and which is not so easy. And you use terms and combine them with Boolean operators. And we have examples for these languages. Messenger, for example, is a retrieval language. I think it was taught in the introduction. Remember? Messenger is a retrieval language. Everybody remembers that? Or nobody? Maybe that is not part of the introduction anymore. Skip for something. Anyway, that's an example for a retrieval language. Here we have a search expression below, and people who have been in the pattern class, they probably recognize some of that, but we'll come to that. Core idea of Boolean logic, of course, is, as I said, sets. For example, we have 3 search terms, A, B, and C, and we have 3 sets, and we can say, there is an intersection of 3 terms. For example, obviously this would be the set of term A and term B and term C, term 1, term 2, and term 3. How can we express this set? Let's check your Boolean language skills, Boolean logic skills, please.
Term 1, term 2, and not term 3.
Yes? Not term 3 and not term 3. And between these two we have? And. Yes, very good. Term 1 and term 2 makes this intersection. Oh, and not term 3. We exclude this little part here, and this is the remaining the remaining stuff. So by using and or not, we can kind of express all of these sets here that are involved and hope that we meet our interest somehow. I can express our interest. There's a lot of potential, of course, using Boolean operators. We can have a lot of different queries. We can have very typical, for example, more or less synonyms that we say, okay, can be either B or can be C, and then we have to intersect it with A. We have a small example for that. I think, yes. And that is an example on how we often work with Boolean operators. We try to define a set until it's a reasonable size. Okay, then we can read it or we have 5 queries here, and here we have the number of hits that we receive. We have our interest. Well, how does cigarette consumption affect the risk of getting cancer for young people? And we start with cigarettes. We get too many hits here. We say, well, we don't want to read 19,000, so let's only use a field search, and we search cigarettes only in the title. It's a little s, right? But we still don't want to read 2,000. Now we look for cancer, the second big thing in this query, this interest. And then we intersect query 2 and 3. and we get the intersection between these two, which is a smaller number, and if we intersect it then with the third facet, we could say, of the interest that we have, we end up with 50, and it's okay. 50 is something I can look through. I'm satisfied for the moment, and I was lucky I didn't get too little, and I didn't get too many documents. There are many systems that still operate with Boolean logic, with Boolean set theory. As I said, the library, and a lot of special domain search systems like this one for educational purposes here in Germany, Fachinformationssystem Bildung, FIS Bildung. Here we have fields. We can define our fields and put our terms. And where does Boolean logic come in? We see, well, here is a brief description of what the Boolean operators mean, how they can be used. And we don't have to type them. You just type here, and within a field we use OR, and between fields we use AND. They just tell us, right? In case I don't like this, I want to reverse it, I might have problems here. I can't actually do it. Okay? So often there is a visual support, but that's typical, somewhat limited also. Again, in the simple search system here, we have one search field. So it looks like a search engine, like a probabilistic or vector space model, but it's not. And here we can see, here we have again a very brief definition of Boolean logic. How will the terms be interpreted? Should they be in all words or at least one of the words? So should it be or AND interpretation? We can specify that. So without really using AND or, we can work with Boolean operators here. Or we have to work with Boolean operators. We can also find it in expert or expanded search, in typical search engines, but it's more and more difficult to find it. There used to be more obvious. Or here a typical library search system again. We have the Boolean operators hidden in a graphical interface. We can also use all kind of additional operators. We've studied several in the patent retrieval class, if in case you there remember. For the others, there is something like phrase search. I want to have that phrase exactly as it appears. I don't want to have Hildesheim and university somewhere in the text. I want it really the phrase University of Hildesheim, Universität Hildesheim, as one, as these two words really following each other in this order. There are also proximity operators that say, okay, I want to have two words in the document, but they should also appear in the same sentence or in the same paragraph, not somewhere really separated from each other. Disadvantages of Boolean logic is quite straightforward. I think that was also already mentioned in the introduction class. There is a strict separation between relevant and non-relevant. There is no in-between. There is no, well, it could be interested, but maybe not really, and it's either that or the other one. Then there is basically no ranking. We don't know which of the documents in the set should be on position 1. There is no information on that. It's either in or out, and there is no order in the As I said, for example, our library uses a formal descriptor to rank the publication date. There's nothing to do basically with relevance. Right? We hope it might be interesting. Of course, there is a reason why they put it. Might be interested. The user might be interested in these more recent documents, but has nothing to do with a relevance ranking. Then the number of retrieved documents can be hard to control. Using OR, I can have a way too large number of documents, and if I use AND, I can have 0, right, easily, if there is no intersection. So it's difficult to really manage to find a reasonable number. Boolean logic is difficult to understand. Well, we had this nice example. We could solve it easily, but we know that users, even professional users, confuse Boolean operators. Why is that the case? What makes them so difficult? We even teach them at the university level to you at the introduction. What makes them so difficult? They look so easy, and or. Everybody should understand and or, right? We even have and or in our language, so what is so complicated about it? Well? Yeah, please.
It does not have the same function as and or in natural language.
Exactly. It's quite different, right? It can be different. Natural language is more flexible. And we have to really learn the proper function in the Boolean world, otherwise it doesn't work. For example, any examples? If I'm visiting somebody and they ask me what they want to drink, I say, well, I want beer or wine. It's unlikely that he brings me both. Right? In a Boolean world, he could bring me both, but that's very unlikely. So we see, there is quite a difference. If I say I want beer and wine, it's quite a drunkard, but he will understand that I want really both at the same time. Let's say I want water and coffee. That's the example maybe, right? Then if you say I want water and coffee, the waiter typically will bring you both. Whereas in the Boolean world, if I want water and coffee, for this example it doesn't even work. Okay, he will bring me dishes. Well, that's not a good example. What else do we have? Well, if we use the search, we want cancer documents with cancer and. I want documents about cancer and documents about cigarettes. Then, natural language, somebody could give me a document that only contains cigarettes and one that only contains cancer. And in a Boolean world, that would be wrong. Okay, so we see the natural language meaning of and or, as I said, is quite different from the logic function, from the logic meaning. And Boolean logic is hard to visualize. Well, it's so easy to draw these nice, what are these called anyway? These kind of diagrams? Venn diagrams, yes. I write it down. Named after some mathematician probably. That looks quite easy. That's easy to visualize and we could easily interpret it. How can I say that it's hard to visualize? Oops. Well. This is a pretty simple example for 3 terms. And if I have 4 or 5, you don't want to see these Venn diagrams anymore, right? And if you have a large number of set, and it gets quite cumbersome, and it's not nice still to work with these systems. Okay. Since Boolean models have these disadvantages, especially that they don't have a ranking, that's quite negative. People have come up with the idea of extending Boolean models. So-called extended Boolean models would then simply make a set, and then a second step, rank this set based on typical weighting and ranking systems. So the idea of expanded Boolean models is Boolean query and ranked output bring together the advantages, which is exactness of Boolean models, and ranked output, which is of course much more user-friendly and much more, very much preferred by users. Boolean queries, by the way, are not only still active in the library, but a lot of professional applications, Boolean models still prevail. Patent experts, for example, 99% of them work with Boolean models. It's absolutely necessary in case they cannot miss really relevant documents. If they have to prove, for example, that they really searched for everything before they invested a lot of money, then typically Boolean queries are preferred. Okay, so Boolean model again here, just visualization. We have a query with AND, or in this case with OR. We have a set, and then we look at the weighting and stuff and make a ranked output based on like the vector space model, which we have here. Another idea is to do something like the quorum level search. The idea is if I have a query with 4 terms, for example, I can use quite a lot of time to make the best combination with AND and OR. And quorum level search would simply do the following. It will create all combinations that have either all the words, or 1 word, or 2 words, or 3 words of these 4 terms. I don't have to worry about that. The system should automatically create these sets and show them to me and say, well, if you really want 1 and 4 and A and B and C and D, the strictest interpretation, you will only get 2 relevant documents. But if you satisfied with only 1 of these 4 words in the document, you have a larger set and in between. Then I can make a decision, well, okay, 2 is not enough, 80 is too much, I'll either go with one of these 2 sets. So again, support for the user by automatically creating these sets and showing them to the user. Understood? Not really difficult, I guess, quorum level search. The next system that we want to look at is fuzzy sets. Before we move into the, well, actually we can start with the ranking. We move to ranking systems. And here we, of course, can have a set of different systems. Now we have to have a rank output. The system thinks that the top document might be really the most relevant one. It thinks, the system assumes, calculated that it's more relevant than the second one, and so forth. And this can be done by a family of systems. We'll talk about vector space today. Mention probabilistic. We'll have on the 8th language models and neural networks, query activation. And today, as also a model that is between Boolean and ranking systems, we'll talk about fuzzy systems, fuzzy sets. Of course, as you know, ranking systems, this is what I just said. We need a weighted index, we need some metric to calculate the weight ranking, and we can have that's the nice thing. We don't have to decide before we look at the I want the 8 or the 23 or 100 documents. We just look at the documents as long as we're interested and as long as we want to. So the user defines the cutoff after he does the query. He doesn't have to think about it before. Much more user-friendly, of course, right? So this is one of the best nice features here. We don't have to decide before on the number we want to look at. We'll have, of course, we have better retrieval quality that has been proven in the 70s and 80s already, 1980s, 1970s, by Zoltan, for example. And this was well researched, but nobody cared. And systems still continue to be Boolean. Commercial systems in the 80s, even early 90s. And only the web with search engines changed the game, and today everything, typically a system would be a ranking system with a partial match metaphor behind it. So the web really changed this, brought it more into the practical world, but something that had already been known before in the research community. So as a first ranking system, we take a look at fuzzy retrieval systems. Here we get a little bit closer to the database world, but that does not matter. Fuzzy sets are an extension, again, of Boolean sets. We say, okay, that's not nice that a object has to be in a set or not. Document is either relevant or not. We should have something in between. We should have maybe best it would be a number that tells me, well, this is in the set, but maybe not fully. And this is also in the set, but only a little bit. So we should have a kind of ranking for the membership, right? Something is a fully member and something is not really full member and something doesn't really belong to it and so forth. So the basic idea is a probability that an element belongs to a set. That's the basic idea of fuzzy sets. Whereas in a Boolean set you can be a set member or not, so you have a membership function of 0, not in the set, or 1 in the set. This is relaxed for fuzzy sets. You can have now a membership function, a value, that can be between 1 and 0 anywhere, and you can be a member of, an element can be a member of the set with 0.3, or with 0, or with 0.9, 0.99, whatever. Right? So we can decide, we don't have to decide yes or no, we can have a ranked membership function, a membership value. Visualization, more or less well here. And as an example, to illustrate that, we use vague queries. That could be almost more or less from also from a database system, but also from a retrieval system. Now we look at vague query operators. We have a query operator. I'm searching for a hotel in Paris in the mid-price range. We have a similar query, or very similar query. I'm searching for a hotel in Peine at mid-price range. Now, what does mid-price range mean? It's a typical something that we use in natural language, right? So, I bought an expensive car, or I bought a cheap car, or I bought a more or less expensive car. I say, well, we can easily communicate. We know more or less what the person is talking about, or we think we know, but we don't have to really state exact numbers. So humans can use these vague operators, these vague terms, very well for the communication, but what does it mean for the computer system? What is interesting about the mid-price range here in these two examples? Is it the same?
I guess the average price for a hotel in Paris is higher than for a hotel in Peine, so the ranges are different depending on the city.
We would expect that it's quite different, right? And that is something, when we talk to each other, that's somehow easily understood, but how can we model that? And for that we can use fuzzy sets. We can have fuzzy functions for these vague expressions like cheap, mid-price, or expensive. Then we make a definition, say, well, in this context, Paris, or in a context, Peine, whatever, we can debate about that. That means something different. And now we have three fuzzy sets. We have a fuzzy set cheap, we have a fuzzy set mid-price, and we have a fuzzy set expensive. Here we have the prices in euro, and here we have the membership function, and we can be between 1 and 0. 1 and 0, okay, this direction. I guess you understood it. For example, the hotel with 20 euros, if there exists one, right, would be 100% within the fuzzy set cheap. The hotel with 40 euros would be to some 0.5, be still a member of the cheap set. But maybe some people would say, for me it's already too expensive. Right? I don't want to waste any money on hotels, so I find it expensive. So it's it's still cheap, but with only 0.5. And it's already a member of the mid-price range. Some people would say, there can also be mid-price range with a value of 0.1 or something. And if we increase the price, we steeply, the membership value for mid-price range would go up. Somewhere it would be 100%, and somewhere it would drop for 100, for let's say 110. Some people would say still mid-price range, others not, and we would have a membership function 0.5. For 110, let's say, we have a membership function of 0.2 for expensive and 0.7 for mid-price. So of course these things overlap, these concepts overlap also in our head. And here we fuzzy sets, we can model that. Of course, where the exact definition is, has to be determined. Now what is your opinion? Is that more the definition for Pioneer or more for Paris? I'm not sure. I haven't visited both cities in a while. So, or for neither one? What do you think? Who has been in Paris last year or something? Nobody? Well, maybe it's a bit too low for Paris and too high for Pioneer. I'm not sure. Somewhere in between. So for Paris we would shift everything a bit to the right, and for Pioneer a bit to the left, probably. Okay. Now, this is just a formal definition of what I just explained. We have a new set of objects, maybe hotels or documents. And one hotel is a member of the set of hotels, and then we have a fuzzy set that is within all hotels, a fuzzy set of the hotels that have, for example, the fuzzy set cheap hotels. And that is defined as a membership function that gives a value to each of the members. Each hotel would have a membership function. Each of the hotels in our universe, Paris maybe, has a function, cheap hotel, that is between 0 and 1. Right? Some hotels are not in this set. The 5-star hotels are not in this set, and the 1 or 0-star hotels, they would be with some high value in this set. And the 2 stars will have a lower value. And this is just a formal way to say that. And now comes the interesting part. Well, it's all interesting, I guess. But now we can also use our operators. Remember, set operators and or, even not, we can use. We have intersection, union, or, and intersection or union, and we have not, always a complement. And now we can define ways. What is the membership function for a set, for an object? Not only to one fuzzy set A, like cheap, and B mid-price. What is it for the intersection or the union? There are different ways to define that. Maybe formally nice, but not completely Okay. What would be how could we define the intersection for the fuzzy set cheap and fuzzy set mid-price? Something we wouldn't ask typically in a conversation. I want a hotel that is cheap and mid-price, right? Doesn't make really sense. We would say somewhere in between or something, but we'll have examples later. We can also, of course, look for cheap hotels that have a good service. Good service would also be a fuzzy function, and we want then the intersection. Now we can, what could be the intersection? Of course, this intersection, right? And basically, the intersection now has to be again a fuzzy set. So we have a membership value. The intersection, the hotel that has the highest membership function in this set is somewhere 0.4 or something. There is no object with a higher membership value. Some with lower, but still it's not very many. If we look for the intersection between cheap and expensive, of course we say all the members have a value membership function of 0. There is no object that has a higher membership value. There is simply no intersection. Well, and if we do that, we can model sets like that, set of cheap used cars, a set of used cars in good shape, and everybody buys a cheap car, wants the intersection, cheap cars and good shape. And then, of course, we could have problems with the weighting of the models, weighting of this concept. Some people would say, well, for me the price is more important, and for others the shape is more important, and these things could not be modeled with simply the definition that we had here. Basically, this is the same definition. It just says, it's the intersection, the minimum value of any of the two sets. So for one object, for one hotel, to be in this intersection, as we define the little thing as we saw on the graph, we use the minimum of the two values in both sets. For fuzzy union, we use the maximum of the two membership functions for this fuzzy set A and for the fuzzy set B. Let's have a look again at the graph, maybe. We have one data point, one hotel with a certain price. Now we see, we want to have the intersection of cheap and mid-price. We see, the mid-cheap, its membership value for cheap is 0.8. The membership for mid-price, is 0. The minimum of 0 and 0.8 is 0. So this hotel does not belong, or we cannot really say does not belong. It's a Boolean expression, Boolean way to think. We say it has a membership value of 0 in the intersection between cheap and mid-price. Right. And if we have a hotel with a price of 50, we say, has this membership value for mid-price, has this membership value for cheap. The minimum is a new membership value for the intersection, for the fuzzy intersection. Right. Okay? Questions? Graphically, it's very easy to look at this intersection, right? And this is just a formal way to express it, use the minimum, or in case of a union, cheap and mid-price, cheap or mid-price, fuzzy or, something that doesn't really make sense. Well, we can say, I want to have a hotel that is either cheap or mid-price, not expensive, right? Could make some sense. Then we use the union, and we use the maximum membership value function. So basically, we would use something like this. That would be the membership value of the fuzzy OR of these two sets. Okay, graphically we can see that very easily, and membership function would be the maximum of the individual membership functions. Okay. So much for Boolean world, for the expanded Boolean and the fuzzy as another expansion of set theory. And now we leave this behind and we come to partial match models. And we'll talk about 3 partial match models. Today, vector space model. Historically, vector space model has already been invented in the 1970s, but it took until the 60s even by Salton in Harvard and Cornell University, and it took, as I said, until the 90s until it had commercial success, and now it's like ubiquitous in retrieval systems. And metaphor, as we said, is simply spatial or geometric close documents that are close to my interest, close to my query point, are relevant. And we think of the collection as a lot of data points somewhere in space, in an n-dimensional space, and then we do ranking or matching by calculating the distance. That's somewhere in the back of our minds. And now how do we find the data point? So closeness means semantic similarity. That is the idea. If it's close, the user will find it interesting for his query. We have data points, and to map that into a Cartesian coordinate system, something you know from school, is the weight of a term is the distance on the dimension. And each term represents one dimension. Example, we have 2 terms, 2 words in this universe now only. Of course, typically, as we said, we have between 10 and 30,000, so we cannot draw it on the board, but we can calculate with it. We can do math with that very easily, but for illustration, we can only use 2 terms. Now we have one term A, and the weight will be marked here. We'll have to calculate the weight based on one of the formulas that we studied last class, including maybe IDF, TF, and length. Then we do some, okay, here we have the weight. Or here we have the weight of in document 2. What is the weight of document, term B in document 2? That's here. And then here is the data point. Same for document 1. And the same for my query. And now in this example, it's quite easy to see what would be the match, what would be the ranking. No, what is the closest to the query? I'm interested in this. This is my query. What would be the ranking?
Document 2 is blank.
It's closer, right?
Yeah,
That would be the simple geometric metaphor. I look for the closest one. And this can, of course, be easily calculated also with simple math. Right? This would be the first one, this would be the second one. So far, so good. So what we need is a similarity. Similarity is like the opposite of distance, right? And in order to do that, we go through the lines of our document term matrix and calculate the similarity. We can also calculate similarity between terms, something that we'll do in a later class still. Here we have another example. Animated. Again, we can look at this. We have a query. We have document 1 and document 2. And now what would be the best fit? Of course, based on what we said before, would be
Before would be document 1 because it was a closing. And now should be document 2.
This seems to be a longer distance, shorter distance than this one, right? Everybody agrees? Okay. Right. Like the same, similar solution to the solution before. But now we could have second thoughts about it. Would really be document 2 the best fit for this query? Why could we also think of document 1 as a better solution?
Because both terms are weighed almost equally.
Aha. Yeah. Uh-huh. We have quite a balanced document, we could say. And for document 2, we have a higher weight for this one, okay. A much higher weight for term A. So why is document 2 ranked higher in this small example? Now think of terminology that we used last week. What is document 1 compared to document 2? One important feature. We talked about it all the time last week. At least the last third of the class. Yeah. Which one is shorter? Document 1 is much shorter. It had only small weights, right? And document 2, has a much longer vector. So it has a higher weights. So that means this comes from probably a longer document. Right? In this case, it's only a good match because our query is extremely long. Think of a typical query, that would be only 2 words, right? And that would be where in our system? Like if this is 1, it would be here, right? Then we could have second possibilities. So we see that this ranking can also be calculated in 2 ways. We can have the distance. This one wins. And now we can think about the length. What could we do with the length? What did we do last time?
We normalize.
Normalize, yes. And what would happen if we normalize the length of all these things? All these 3 objects. And in spatial metaphor, normalization is very easy. It's just to
Make them in the same length, approximately.
yeah, just identical length. Let's make a simple assumption, not about pivoted length normalization, stuff like that. Let's make it easy to begin with. Then all these vectors just would be scaled down to 1. Normalization here is very easy. Zack, zack, zack. And all will be around here. Right? And if we, in case we normalize, which document would win? Not so easy to see. What? 1 would win, yes. 1 would then be closer. Right? If we assume normalization ends here, right, we would say, aha, here, 1, this is here, aha, this is larger than this. And how can we see that without normalization? We'll have to normalize.
Maybe if you calculate the areas between vector document 2 and query and compare it to the area.
This area?
Yeah, exactly.
Yes, yes, yes.
And maybe if you just compare to the area between document 1.
Yes, the
these
area.
triangles.
That would work. Yes, but there is an even simpler mathematical way.
The angle or
The angle. Yes, the angle. Winkel, huh? The angle between the vectors, which is basically the same, but it's so easy. we see that this is a larger angle than this one. So the direction of this document is more towards my interest, expressed by the query, and this is a bit off my query. Right? So with length, with normalization, or with angle-oriented metric, document 1 would win over document 2. So we see that we have a simple spatial metaphor, as I said before, but basically we could have two metaphors in a spatial world. In a geometric world, we can have the distance or the angle. Right? And we have two matching functions, two pure matching functions. One is Euclidean distance, document 2 wins, or we can have simply the angle. Or for a larger angle, how do we, talking about angles, what do we like to calculate? 6th, 7th grade, maybe math. Cosine, right? We calculate the cosine. We have a larger cosine for the smaller angle, higher similarity. The similarity is higher because the angle is smaller, cosine is higher, so cosine is a good approximation for similarity. If we do cosine, document 1 wins. If we do Euclidean distance, it's even before 4th, 5th grade maybe, right? We have document 2 wins. So again, we see a lot of options for us. What do we do in the end? What do we do? We can do so many different things. We can use TF, we can use the logarithm of TF, we can use IDF, we can use length normalization, pivoted length normalization with different kinds of parameters. Now we have two ways to match angle or distance, right? It's already 8 options, and some of them can be combined. So we already, only 2 classes, we can implement like 100 different retrieval systems, and we don't know which one is the best. So we'll have a class on evaluation, don't worry about it, and we'll see how can we at least look for the better system. But what would be the best system? Well, we don't know, right? And what most retrieval systems do is, again, what could be a suggestion? Something similar to the pivoted length normalization, we make a compromise. Right? Most metrics are somewhere in between this. We can have a purely distance-based metric, Euclidean distance. Here is the angle, again, okay. And we can have the other pure form with the cosine, just using the angle. These are 2 functions that can be used. Cosine is in every retrieval library, probably also in Lucene. We can use any of them. But in reality, most other functions that calculate similarity are a compromise between the 2. And plus, consider, we have to remember what we did in weighting. If we normalized, fully normalized when we did the weighting, it doesn't matter. Then both would lead to the same result. If we squeeze all the vectors to length 1, then it doesn't matter. If we use pivoted, again we would have to look, what do we decide on, right? And we know that pivoted length normalization is better because it's in Okapi has some form of pivoted metric. So another decision we have to make. For example, here the cosine purely cosine between document and query in a purely angle-oriented way. This is the way to calculate it. And we see that we have the length normalization within the cosine already again, because we divide by the sum of the lengths of the documents. And on top we have now the sum of the products between weight in query and weight in. Let's assume the weight in the query is always 1. We can easily assume that user types 2 queries and doesn't give a weight to Wolf or to Niedersachsen. It's both important for him, he doesn't worry. So it's 1. And then we have a lot of all the terms that are not in the query. For in our example, Wolf and Niedersachsen, we had some documents with Hildesheim and some Hannover, and they have another 10,000 words maybe. But the query weight for all these is 0. The user is not interested in it. It's not in the query. Only 2 words are in the query. So for all the other ones, this is 0. We don't even have to look for the weight. We have the weight for Wolf, in the query is 1, multiplied with the weight for Wolf in the document. And then plus, then we use the sum of the weight in the query for Niedersachsen now, 1, plus the weight of Niedersachsen 1. So here we use the sum. If we use cosine, we would do length normalization, but more or less we would do something like we did on the board for the example Wolf Niedersachsen when we did the sum. Dice metric, of course, we can also have the distance metric, the Euclidean distance, that's easy. Dice metric is something in between. We have a kind of a length normalization part here. We have again the matching, very similar to cosine, but 2 times. That's actually quite similar to the metric that you use in the homework for the n-gram. Right? That's a very similar formula. The length of one document plus the length of another document, which is the sum of the n-grams, 2 times the overlapping n-grams, 2 times the weight, the multiplied weights. And there are hundreds of similarity metrics for Cambridge-Jacquard. It's also used a lot. Again, works differently. And they all, as I said, are compromised between the 2 pure forms, distance, angle. So, questions so far? Well, so far, only 10 more minutes anyway. Not the case. Again, we'll repeat this next time with the weighting stuff and do some calculations by ourselves so we can fix this stuff. Remember that better then. Now some more remarks on the vector space model. Basically, it's a heuristic meta model. If we talk about the vector space model, we can also some way talk about the probabilistic model. We have a theoretical and practical problems. The theoretical problem is independence of terms. We assume that terms are independent from each other because they have a 90-degree angle. They don't have a relation. And we know, of course, this cannot be true because terms like cat and dog are more related than cat and car. Right? Oops. There is obviously a problem there. It's very straightforward, easy to understand. You can easily understand the vector space model in one class, as you did now. The probabilistic model goes one step further. We don't really will deal with the probabilistic model in detail because I assume it as one submodel of the vector space model. There we have probabilities. We talk about probabilities. Remember the joint conditional probabilities. Basic formula in statistics, and for information tree we simply interpret the weight of a term in a document as the probability that this document is relevant for a query with this term, right? Just like similar to the Boolean idea. If I query with a set, I create a set of documents with this term. This is a relevant set. And in probabilistic retrieval, basically I would say, well, this is the probability that I get from the weighting that this term is relevant for a query with just this term. The ranking idea has been formulated in a probabilistic way. We would have, of course, probabilities between 0 and 1. That's something we don't have in the vector space model necessarily. But we could transfer that and normalize that to that case. And we say the probability ranking principle says, well, it's good to rank documents in a collection in order of decreasing probability of relevance. So the most document with the highest probability for relevance is the top document. And the probabilities are estimated on the basis of whatever data is available. This is quite general. So far we assume the only data is available is the weighting information based on the term counts. We count and then we calculate our weights. And then we rank. So P, relevance of for a document, the relevance of a document to a request is independent of other documents in the collection, also an assumption that is made here. But, and that is why we can allow us to not go too much into the probabilistic model, is the assumption by Turtle and Kraft. Kraft in 1992, he says, well, we show that the theoretical papers about the theoretical discussion about probabilistic models and vector space models, that these are basically essentially equivalent. And even exact match models, like the Boolean models, can be seen as a special case of the vector space model. We can now say the Boolean model is a vector space model where we have only two weights, 0 and 1. And the probabilistic model is also just some sort of vector space model. So Turtle and Kraft say, if we study the vector space model, we can basically cover this whole family of models, and they're more or less the same. Discussion about models has lost its importance. Nowadays, we assume that it's not the model that's really important, but all these heuristic components that we have. We had stemming rules now. We had stop word lists. For each stop word list, I might get a different result. We have our heuristics, we have weightings. Do we use PF? Do we use IDF? How do we use it? Do we use a logarithm? Which logarithm do we use? And what kind of similarity functions do we use? So, as I said, we have many, many heuristic definitions, and the model doesn't really help us in which one of these should we select. Only experimentation, further experiments, evaluation can tell us which system is the best for a special application. Nevertheless, on 8th of June, we learned some more about models, but different families and quite interesting models. Okay, so today there is no homework, then there is no class for 2 weeks, but then there will be homework 3 weeks in a row, and always some calculation. Next time we do weighting, homework on weighting, then we do language models, there will be something on language models, smoothing language models, and then maybe we do web retrieval first and then evaluation, and we have 1 week without homework maybe. Questions? Not the case, so see you then in 3 weeks again. Thanks.